Force problems number 2. We're going to go through 2 more force problem examples. Again, we're kind of going to hopefully hit the highlights of the different types of forces that we're talking about and when they apply and when they don't apply through these. And again, to go back, there's things that we should know ahead of time. We should know the equation for force of gravity. We should know the force of gravity is always down. We should know the normal force is the force that stops an object from falling through the surface. We cannot say that it's always equal to the force of gravity, right? It's going to vary for each situation. We should understand that, right? So the normal force is the force required to stop an object from falling through a surface. So we want to keep that in mind. Friction is always in the opposite direction of motion. We could either have kinetic friction or static friction. Again, we're not going to have both. And then the last one, the sum of forces cause an acceleration, not a velocity, right? So forces can cause something to accelerate in a certain direction. That doesn't mean they're necessarily moving in that direction at this moment in time. All right, so let's look at the first example. Find all the forces and the acceleration. So I look at this, I have a pulley, and I have these 2 masses that are hanging from one rope on this pulley. So first of all, let's just look at the pulley. So let's first talk about the pulley and what is a pulley. So a pulley has a unique job. A pulley allows us to change the direction of a force. So a pulley changes the direction of a force. But what it doesn't do is change the amount of force. So it changes the direction without changing the magnitude, without changing the amount. So that's what a pulley does, right? And this is an ideal pulley if we're assuming the pulley works well. There's no friction inside it or anything like that, which is not a poor assumption, really. There's plenty of pulleys that do their job very well. So it changes direction without changing the magnitude. So that's what a pulley does. So we're going to put numbers for this, but if this side, the rope is pulling down with a force of, let's say there's a force of 15 newtons on the rope on this side. Well, it's only one piece of rope, so what's over here? Force of 15 newtons. So that's what a pulley does, right? It allows the forces to be in different directions, but it doesn't change the amount of force, which makes them very useful. All right, so we have these 2 blocks. Let's take a look at them. I'm going to do the first one, the 5 kilogram block on this side, and I will do the 8 kilogram block on the other side. There we go, 8 kilogram block on this side. And let's draw force diagrams. Now, the force diagrams are fairly straightforward. It's amazing. Not amazing, right? But it is, there's a lot of forces that people want to put into these equations or put into these situations that simply aren't there, right? The normal force is the force that stops an object from falling through the surface. Well, there's no surface that these things are touching or trying to fall through, so there's no normal force. If there's no normal force, there's no friction, right? So a lot of the things that we just talked about are things that we learned in class. They don't exist in this. Gravity's pulling down, and what's pulling up? Well, the force of the rope is pulling up. I'm going to call it T for tension, which is basically the force of the rope. And I look at this and I say, okay, the sum of the forces is, well, tension is up minus the force of gravity, and that's my sum of the forces. Now I'm going to add a little bit to the left side, though we know Newton's second law, sum of the forces equals mass times acceleration. So I'm going to look at this in a second, but this is what I have. The up is positive, the down is negative. I look at the other one, well, force of gravity is down, and tension is up, so that didn't really change anything. And at least for starters, I could say that the sum of the forces is the force of gravity, or tension minus the force of gravity. Again, I'm going to leave this for a second. But at least I have the sum of the forces part of the equation. Now, like we were saying in the last one, we want to make these equations with the directions in it. And I've already put the directions in there for tension and force of gravity. And like I normally do, I've made up positive and down negative. But I have to do the left side of the equation too. And to do that, I have to make an educated guess. Now, this one's not that hard to make an educated guess, but really what I need to do is I need to have both of these equations agree with each other for this situation. So if I look at this, I have an 8 kilogram block here. I have a 5 kilogram block here. Yes, I know gravity's pulling down on both of them, but this one has greater weight. The force of gravity is more. So I'm going to say that this one is going to go down, which means this one's going to go up, right? And I have to do this when I'm writing the problems. I have to look at the situation and I have to make some assumptions of how things are moving. And then sometimes it's easy, sometimes it's harder, but it doesn't even matter if I assume wrong. The only thing I can't do is assume an impossible situation. So if I said, you know what, I'm not sure if this is right, and I think that this one should be going down and this one should be going up, right? That would still be okay. What would happen is it would give me answers, and when it gave me answers, those answers would be negative, which would be saying, hey, these are the numbers that you're looking for, but the direction's the opposite of what you thought. What I can't do is make them both going up. I can't assume that both of these blocks go up, because now it just shows I don't understand the situation. If I don't understand the situation, I can't solve it, right? So it's impossible for both of these blocks to go up. It's impossible for both of these blocks to go down. So as long as I don't make these equations based on something that's impossible, I'm okay, right? So if I said the 5 is going up, well, then the 8 has to go down. If I decided that the 5 is going down, well, then the 8 has to go up, right? Those are my only two choices. I'm going to go with the red ones because that makes more sense to me, right? The 8 kilogram mass is going to have more weight to it, which means it's going to win in this pull between these two. It's going to start going down. So that means the 5 is going to go up. So with that said, I said up is positive, so this is going to be MA. And I'm going to keep this all positive because it's going up. I look at this other one, it's going to go down, so that means I have to make this side negative because the acceleration is going to be down. Now, I could put the acceleration in between the M and the A, but in the end, if there's a negative number, this whole thing is going to be negative. So these are my two equations. And again, this is up, this is down, this is up, positive, negative, positive. This is up, this is down, this is down. That works out to positive, negative, negative. So that's what I have for my directions. And again, that works out well as long as I make sure I stick with those directions, right? Or as long as I make sure those directions make sense with each other. So that becomes important. They have to make sense. All right, I'm going to start filling in things I know. Well, I don't know T, but I do know the force of gravity here. It is 5 times 9.8 or 49 newtons equals the mass, 5 kilograms, times A, and A I don't know. It's the best I could do with that equation. On the other side, I still don't know T, but it is 8 times 9.8. So the force of gravity is 78.4. There we go. 78.4 newtons equals negative 8 kilograms times A. So I think I said this before, but just to say it again, I'm doing all of these situations, or I'm making all of these equations with the directions in them. So I'm not trying to solve for direction. If I make the equations with directions in them, all I'm solving for is the amount. I know the directions, right? If I decided to write it like this, and I decided to write the other one like this, and I decided to ignore all directions, I said this is true and this is true. These statements are still true. But the problem is now when I'm solving for things, I'm solving not only for the amount of force, but I'm solving for the directions of the force. And this becomes a much harder problem if I'm trying to get both pieces of information from a situation that's even as complicated as this, right? So we know the situation, we need to put the directions into them. So I'm going to get rid of these because these are just not as useful to me as the equations I made. All right, so I have two equations with two unknowns. There's more than one way to solve this problem, but I'm going to do it my way, right? But there's multiple ways. I could solve for t in both cases, set the equations equal to each other. I could solve for a, right? I could solve for t in the left one and substitute in the right one. I could solve for t in the right one, substitute in the left one. Solve for acceleration in one and substitute in the other. So there's what? At least 6 different ways I could solve this problem. So I'm going to do it the way that I would do it. So the red equation, t minus 49 newtons equals 5 kilograms times a. I'm just writing the same thing that I had before. And the other one was t minus 78.4 newtons equals negative 8 kilograms times a. And I'm going to solve for t in this equation and substitute it into the other one. So I'm going to add 49 newtons to both sides. So it's going to be 49 newtons plus 5 kilograms a. I'm going to take all of this, I'm going to substitute it in for t over here. So it's going to be 49 newtons plus 5 kilograms times a, and then still minus 78, minus 78.4 newtons equals negative 8 kilograms times a. All right, so here we go. I look at this problem. I need to solve for it, so it's going to be 49 minus 78.4. It's going to work out to be 5 kilograms times A minus 29.4 newtons equals negative 8 kilograms times A. And then I'm going to move this over to there, so I'm going to add it to both sides. I'm going to move this over to there, so I'm going to add it to both sides. So I'm going to have 5 kilograms A plus 8 kilograms A equals 29.4 kilograms. And this works out to be 13 kilograms times A equals 29.4 newtons. So I'm going to have 29.4, and a newton is a kilogram, meter per second squared, divided by 13 kilograms. .26 meters per second squared. So there's my acceleration, and that's my acceleration for both of them. And again, this acceleration doesn't mean up or down, because when I look at this situation, one's going up and one's going down. What the positive means for this is it's telling me you're right in the directions you put into the equation. Your directions are right. If I got a negative, it would tell me, hey, this is the acceleration, but the directions you picked were wrong. It's backwards, right? So we picked the right direction, and that's great. But it would be no tragedy if we picked the opposite. Now, the other thing that I could solve for is t, and I have two different places where I could solve for t. I could solve for t here. I could solve for t here. Both of them should give me the same answer. So let's try the red one and solve for t. T minus 49 newtons equals 5 kilograms A. So I'm going to have t minus 49 newtons equals 5 kilograms times 2.26 meters per second squared. Works out to be 11.3. So T is going to equal 11.31 newtons plus 49 newtons. T is going to equal 60.31 newtons. Now I rounded a little there, but it should be okay. So I'm done. I figured out the acceleration. I figured out the tension of the rope. I mean, to be honest with you, I don't even think I listed the question. I'm just figuring out everything that I could figure out, which are these two things. Now, just because, let's just see how it works here. And I'm not really solving for anything anymore. I'm just putting everything in. I'm going to do it in black just to make it separate. So T, I'm saying T is 60.31 newtons minus 78.4 newtons equals minus 8 kilograms times 2.26 meters per second squared. So 60.31 minus 78.4 works out to be a negative 18.1. On this side, I have negative 8 times 2.26 works out to be a negative 18.1 newtons. So I didn't find anything new here, but this also checks out. So every equation I made works, which tells me I'm right? My acceleration's right, my t value or the force of the rope is right. So I've done this problem. So let's say we have this situation. We have a car driving down the road, and the person driving the car slams on the brakes trying to come to a stop. This car slides down the road, right, in the process of coming to a stop. We want to find two things. We want to find the acceleration and the time it takes to stop. We could ask for more. We could also ask for how far did the car slide, right? So there's more questions we could ask, but these questions are fine. Now, I look at this and I say, okay, great. I want to find the time to stop and I want to find the acceleration. So time shows up not in any force equations, but it certainly shows up in our chapter 1 in our motion equations. And I know that acceleration equals final velocity minus initial velocity divided by time. And when I look at this, this is a good equation to pick because what do I know? I know the initial velocity. The car was initially going 40 meters per second, which is relatively fast, right? And I know that the car is going to slide to a stop as I jammed on the brakes. So I know that's 0. I know what this is. If I rewrite this equation, time equals negative velocity initial, and it's negative because it's 0 minus the initial velocity over acceleration. So if I can get the acceleration, I can solve for the time it takes to stop. Now, this makes sense to me because I'm going to have to deal with acceleration because what does the sum of the force gives me? The sum of the force always gives me the acceleration. It doesn't give me the velocity, it gives me the acceleration. And that's just what I'm looking for over here. So this makes sense that I can solve for this by first treating this as a force problem, finding the sum of the forces and therefore determining the acceleration. And then I can do this other part with the motion equations. I could solve for time. And again, if I knew the time and I knew the acceleration, then I could plug these into the displacement equation. I could figure out how fast was the car. I could figure out how far did the car slide while it was coming to a stop. I could figure out all kinds of things. Now, I'm already seeing somewhat of a problem because this sum of the force equations has mass in it. And one thing I don't know is the mass of the car. So because that's the case, for some reason, the mass of the car should not matter. And we're going to have to look at this and we're going to have to see, okay, hey, this is where masses cancel out, right? So mass can't matter because if it did matter, I wouldn't be able to solve this problem because I wasn't given a mass. So we're still going to look at this in terms of forces, and let's make our force diagram. So I know there's a force down of gravity. We know there's a force up, which is the normal force. And it is moving to the right as it comes to a stop. So kinetic friction, because it's sliding, must be to the left. Now, when I do this problem in class, I'll go around and I'll ask, give me a force, give me a force. And there's always a bunch of people that want to give me a force applied. And I say, well, of course there's something pushing it to the right. It's moving to the right. But no, again, forces in motion are not related that way, right? So the sum of the forces causes an acceleration, not a velocity. So the fact that it's moving to the right does not mean it's getting pushed to the right. And the fact that it's moving to the right does not mean the sum of the forces is to the right or the acceleration is to the right, right? These things cause velocity to change. But just by looking at something's velocity, that doesn't give us any indication of what the forces are. So this is my situation. These are the forces I have, right? And when I look at it, I can say, okay, well, what do I know? Well, I know the normal force and gravity cancel each other out. So if I have the normal force plus gravity plus kinetic friction, well, the normal force plus gravity equals 0. 0 plus kinetic friction is the kinetic friction. So kinetic friction equals mass times acceleration. And that's based on Newton's second law. When I add these three forces together, what I'm going to have is whatever the kinetic friction is, because the other two are going to add to 0. So here's an equation based on Newton's second law. Now, we're going to have to make another equation because that's not going to be enough to go by. And what else do I know? Well, I have an equation for kinetic friction. So I'm going to have to know what the kinetic friction is in order to solve this problem. I got a mu value. I've got some other parts of this, so I also know that kinetic friction equals mu times the normal force. And I know what mu is, so that's great. Now, I don't know what the normal force is, but I could think this through a little more. In this case, the normal force and gravity have to be the same. And I know this because the car's not flying into the air and it's not falling through the ground. So the normal force is not winning, throwing it into the air, and it's not losing, letting the car sink into the ground. They're equal to each other. And that means that whatever the value is for the normal force is equal to the value for gravity in this case. And I know how to calculate gravity. It's mg. So I've made a jump and I've rewritten the normal force in terms of what it is in this situation. In this situation, they are equal to each other. Not every situation, right? In this situation, they are, though. So I know this is true about kinetic friction in this case. All right, so fine. I'm looking for acceleration, and I know that mass times acceleration equals the kinetic friction. Then I also know mu times mass times g equals the kinetic friction. So what can I do with those two equations? Well, I could say mass times acceleration equals mu mass times gravitational acceleration, because I've made two different equations that have to do with kinetic friction. And when I look at this, well, what's the first thing I see? Well, if I divide both sides by m, well, that's very faint. If I divide both things by m, then m simply cancels out. So here and here, I could simply get rid of this. And what am I left with? Acceleration equals mu times g. And that I can solve. Why? Because I know mu, it's 0.8. And I know g, it's 9.8 meters per second squared. So what's my acceleration? My acceleration is 9.8 times 0.8, 7.84. My acceleration is 7.84 meters per second squared. And just to say it, right, the sum of the forces kinetic friction, which is to the left, so it's mass times acceleration, which is to the left, so my acceleration is to the left, right? And I could have put all of these to the left if I wanted. I could have made them negative if I wanted, right? But I know the direction of the kinetic friction, and that's the same direction as the acceleration, 7.84 meters per second squared. So when I start to solve for time, well, time is negative 40 meters per second because it's negative the initial velocity. But if to the right's positive, well, here's where it matters. I have to make it negative because it's in the opposite direction, meters per second squared. So this negative is due to this, right here, part of the equation. This is negative because the acceleration is in the opposite direction we're moving. We are moving to the right. We are accelerating to the left. Got to make it negative. And that's important because what happens when I have negative 40 divided by negative 7.84? Well, the negatives cancel out. I'm left with a positive time, right? What happens with the units? Well, meters cancel out. This cancels out one of the seconds up top, so I am left with a positive number, and the units are seconds. Both things are good indications that I'm right. How long will it take to stop? 5.1 seconds. It's actually a long time for something to stop, right? The mu value for the road and your tires is probably much more than that, which will be more friction, which means a shorter time to stop, right? Because that means 1, 2, 3, 4, 5. That's a long time to stop, right? If we see a car accident, things don't take that long. But in this case, with these road conditions, that's how long it would take to stop if we were sliding and mu is 0.8. And again, the mass of the car doesn't matter. If this is the mu value, if this is a measure of the tires to the road, well, then whether it's a big car, a little car, a truck, this is going to be how long it takes to stop. All right, so these are the other two problems that I was going to do. We have a situation here where mass cancels out. We also have a situation where there is no friction, there is no normal force, right? And there is no applied force. Matter of fact, both of these cases, there's no applied force, right? They are simply cases where we let gravity and the other forces that we know do what they're supposed to do, and we don't even look at applying any extra forces to these situations. Okay, I hope these helped.